Hey, I'm Drew. My slides aren't as colourful as the first presentation, but I'm a developer on the Confluence front-end platform team. We're a team of 4 developers that are responsible for the Confluence front-end architecture that the other Confluence front-enders use to make their features. For anyone that's not familiar, I hope everyone is though, but Confluence is Atlassian's wiki and document collaboration software. Over the past 18 months, we've been making big changes to our front-end architecture to improve Confluence for the cloud, and we've learned quite a lot of it along the way. Give me 1 second. Sorry, just trying to find my mouse. Yep. Broken finger from basketball. Sorry, I'm just trying to find my mouse so I can scroll down here. Give me 1 second. Sorry about that. Okay. Just trying to scroll down. Okay, got it. So today I'm going to be talking to you about the different features of webpack that we've been using to optimize our JavaScript asset caching. I'm going to give you 4 different levels of optimizations that we've gone through for Confluence that should hopefully give you enough to go and kind of Google extra things and find the bits that are relevant for you, and they're just kind of tidbits to get you started. For those of you that haven't used Webpack before, it allows you to bundle JavaScript assets together into one file, which is considered good practice for performance because it reduces HTTP requests, although HTTP2 is kind of changing that as well. Starting with a simple app, you can run Webpack, which will bundle the app together and its dependencies into a single file. And in this case, it's called bundle.js. We can then ship this to production and our app's JavaScript is up to date. This is usually sufficient for a personal website or your Heroku resume or whatever you've got, but not really for commercial software. In a real project, we'll probably start adding things like React, Redux, and Lodash, and suddenly we find like the 50 kilobyte app that we started with is now like 2 megs or something bigger. And 2 megs is obviously way too much for people to be downloading on every page, and you'll end up getting bad feedback from users about performance. Thankfully, Webpack has an inbuilt feature that helps solve this problem. So the only thing that I've changed in this example is to add a hash parameter to the output file name, and Webpack will now generate a bundle with a unique hash based on the content of the bundle. That means whenever we change our app, the hash will change as well, which allows us to add a long cache expiry header for the browser. That can really be effectively a never expires cache header. With these 2 optimizations, users shouldn't need to download the bundle more than once. That's perfectly fine for an app that's released and never changes, but it has significant pitfalls that don't really work well with frequently released software. So basically, any change we make will cause the whole app bundle to invalidate the cache, and then it'll need to be re-downloaded. So if you're deploying multiple times a day into production, it'll pretty much make this optimization irrelevant if you're going out regularly. Webpack has a few options to solve this problem. The one that I'm going to focus on is using what's called a vendor chunk. So in this step, I've added a Webpack config and created 2 entry points instead of 1. So we have vendor and app.js in these cases. Vendor in this case becomes, I guess, a dependency for app.js. And by separating the vendor and app entry points, you can isolate infrequently changed parts of the code away from feature code that changes more often. And the vendor.js will usually just include common dependencies like React, React DOM, Redux, the things that don't change very often. This means that the hash of your vendor file will only change when you bump a version of a dependency. So if you're writing a React app, the vendor assets, as most of you know, will kind of make up the majority of the app. And so usually it's a really good optimization. A lot of apps will usually not have to make any further optimizations beyond this one. However, if you're doing a large-scale single-page app, this approach still has a problem. So it's still susceptible to kind of the first issue, which is the app can slowly grow over time and become far too large. And that's just because your app code is still effectively all in app.js, just excluding your vendor libraries. Webpack has a feature called code splitting that can help with this. So you can create a code split by wrapping your logic in a require.ensure, like in this example, and any dependencies inside the callback will be added into a new code split. In this example, the result will end up being called deferred dialog.js. That's the third parameter you see at the bottom. By splitting or picking logical splits in your application, you can start to chunk down the page weight without introducing a huge amount of complexity into like your logic, and it's kind of a conventional pattern to do so. And these splits are often based on user interactions. So for example, it might be when you're transitioning to another route in a single page app, or when a user clicks a button to launch a dialog, like in this example. Deciding how to chunk your app up is something that you kind of get used to over time, just as you become more experienced with Webpack. However, this one also still has a gotcha. When you create code splits, Webpack actually maintains a manifest of splits internally as an object. And if you're using the vendor chunk, like I described in the previous slide, Webpack ends up putting the manifest into the vendor chunk itself. That means that new code splits will actually end up invalidating your vendor cache, and we're kind of basically back at level 1. The gist of solving the problem is that we need to use a plugin to get the manifest out of vendor.js. We kind of found out this the hard way, which sucked. I won't really go into the detail of how you do that, but there's a GitHub issue that I've linked here which goes into the details of some of the solutions. Once we've completed this optimization, it means we'll now have a consistent vendor hash that should rarely change, and small code splits that are requested at runtime, and will only invalidate if you ship a change out to production. And in Confluence's case, we then ship these to S3 and fronted by CloudFront. At the moment, we have a 30-day expiry on those just as a safeguard for our caching, but really that could be never expires. And we're looking at further ways to cache using things like service workers, so actually caching these forever in the browser using some modern APIs. I know this has kind of been a really quick overview, but hopefully it gives you enough info to investigate things further. And if we have time, I'll take some questions. Otherwise, I'll hand over to Lucy. Yeah, John? Anyone have any questions?